So after seeing what that last talk about SkySpark and all the problems of working with real buildings, my topic is kind of now for something completely different, or the fancy schmancy controls that people are talking about in the future. So what I'm going to talk about is my talk's a little California-centric, so I apologize for that. But we like to think that we're kind of dealing with the future energy system that hopefully eventually will be kind of spread all around the country. So I'm going to talk about controlling buildings to help with both distributed energy, like on-site solar and storage, and also grid interaction for demand response and other sorts of grid interaction. So, so the motivation for this is really several different factors going on, or our energy system is changing. And Marianne's going to talk a lot more about this, but show of hands, who's heard of the duck curve? Yeah, I think it's whoever named it was really brilliant, because I think it really sticks in your mind. But the idea is essentially that with more and more renewables going on the grid, particularly solar, that produces a lot in the middle of the day, what we're seeing is this kind of sag in the net load, what they call net load, that the California system operator, the grid operator, sees. So net load is kind of the demand from all the buildings and factories minus the renewables that are kind of non-dispatchable. So what this is saying is whatever is represented by this curve has to be met by power plants that the grid operators can actually call up and say, okay, generate. So the nuclear plants, the gas power plants. And so this causes problems because power plants generally, the thermal power plants, don't like to turn on and off and ramp up and down. And what we're asking them to do is essentially, run a lot at night, and in the middle of the day, turn down or turn off, and then rapidly come back up in the afternoon. And so the grid was really never designed for that. So this is one problem that this kind of new energy system is causing for us. Another factor going on here, as you're probably aware, California has a lot of different policies for deploying new energy technologies out, rooftop solar, energy efficiency through utility demand-side programs. There's all sorts of policies and programs to encourage energy storage. There's EV incentives and all sorts of electrification programs that are starting up now. Because for climate change, to meet our climate change goals, one of the things is the policymakers want to get rid of natural gas in buildings, because that's one of the sources of carbon that ultimately is going to have to be kind of taken out of the building sector. So when you look at all these new equipment that are going into buildings or on top of buildings, what we're realizing is that buildings are no longer these static energy users or consumers. That they really, they could be producing, they could be charging or discharging storage, they can be, the electric vehicle could be there or not be there in some cases, or in some plans, electric vehicles would be able to discharge to the building to help cover some of the loads. So you get this sense of this very dynamic, variable, hard to control collection of equipment. So that's another challenge that we're facing with our new energy environment. And a third thing that's going on is climate change is actually happening. So this illustration here is showing those are the summer peak temperatures in California, both historical on the left, and then kind of in the next decade or so in the middle, and then maybe 50 years out on the right. And you can see, it's pretty obvious, it's getting hotter. And so that drives up the demand for air conditioning. So more buildings, like along the coast that don't currently have air conditioning, will have air conditioning, and it's going to be used more intensively. There's going to be more heat storms, things like that. At the same time, we have more natural disasters from, this is on the East Coast, but hurricanes and other sorts of high wind events that take out the power system. Here in California, this fall, we had the power shutoffs that I think most of you heard about. This is a map of up in Northern California, the power shut off in one county. And so buildings are more and more having to deal with these kind of extreme environmental conditions. And ultimately, we want our buildings to be resilient, right? And even in conditions where the power is shut off or it's really hot outside, we want to be able to be comfortable and have refrigeration and all the other things we expect from our buildings. And so that's part of the challenge, is how do we design and operate our buildings to be able to kind of survive under these conditions. So given all these factors and things going on in the energy system, what the kind of the hypothesis here is that managing the energy use of buildings is one potential solution to all these different problems. So in the case of the duck curve, ultimately the grid is there to meet the demand caused by buildings, right? So if buildings can change their demand, it'll help with that duck curve shape. Similar thing with integrating all these new technologies. These are all kind of coming into the building, need to be managed by the building. And so if we can optimize their operation, that will, taking into account the varying demand and these different environmental factors, it'll help us better integrate these. And if we can operate all these different distributed resources, the storage, the loads, the generation, if we can operate those in kind of a harmonious way where they're all working together, either to reduce our bills, reduce the emissions, either air emissions or carbon emissions, or to try and provide some sort of service to the grid, then that's going to help this future energy system function better. So those are kind of the goals of kind of in the future. Some people call it intelligent buildings or smart buildings, but the idea is essentially that you're trying to serve a lot of different needs by kind of actively and smartly managing the energy use of buildings. So what I'm going to talk about now, the rest of the talk, is about this particular technology, model predictive control, which probably a lot of you have heard of. It actually comes from industry. And the idea is essentially, if you look at, let's see, is there a pointer on here? Yeah. So if you look at kind of this middle set of boxes here, this is what you have in a traditional building, right? So Chris was talking about, for instance, the thermostats out by the window. So you have local controllers, zone controllers that have a particular set points, and they're acting on a real building. And there's some sort of a feedback loop here where the building, performs in a certain way. It's either comfortable or it's not comfortable. And there's a sensor or maybe a small number of sensors that are feeding back to the controller, and you get a certain set of performance. If the world were very predictable and well-behaved, that would work well. But in fact, we have disturbances, right? We have occupants coming in and out of the building. They're opening doors. We have sun coming in the afternoon when it's not here in the morning. We have other sorts of weather, clouds and cloud cover and wind and things like that. So the controller is always reacting to those sort of external influences, and it's always kind of behind the curve, you could say. So what model predictive control is about is, let's build a model. In this case, it's either some sort of data-driven model or what we call a physical model. You're actually mathematically modeling how the building is, the physics of the building. And what you're doing is using that to predict ahead, make a prediction about how the building will perform over some future time scale, the next hour or the next day. And then based on that prediction, you're optimizing the performance of the building. So you're saying, okay, if I change the set points in some way, I can reduce my energy bill. Let's say it's going to be colder tomorrow than it is today, and so I know that my heating is going to be increased. So I want to try and ramp up sooner to anticipate that. Let's say that might be one kind of scenario that this could be used for. And so this optimization is subject to constraints, and you have certain objectives. You want to minimize your energy use or your energy bills. You want to minimize greenhouse gas emissions. There's different objectives you can have. Usually you're just trying to minimize your bills. We had this discussion earlier about, is your customer going to be happy if you're saving energy or keeping them comfortable? Well, that kind of comes into these objectives. And actually through this more explicit modeling framework, you can actually trade those things off. Trade off some comfort for bill savings, or trade off some comfort for energy savings. And so the other thing this allows you to do is have forecasts of what we call disturbance, but weather forecasts, occupancy forecasts, things like that can feed into this. You can take account of that. And then you can have other sorts of signals. In this case, grid signals, demand response signals, you can take that into account also. So if there's going to be some sort of demand response event tomorrow afternoon where I need to reduce my energy use or my power draw from, let's say, 2 p.m. to 6 p.m. tomorrow afternoon, that can get factored into your prediction and your set points so that you anticipate needing to reduce demand later in the afternoon, and you can pre-cool the building or take other sorts of actions. So this is kind of, overall, this is the concept of model predictive control. So it's basically using some sort of model of the building, which could be, again, either physical or statistical, and you use that to predict ahead how the building's going to perform, and you try and optimize its performance based on that prediction. Any questions about this before we move on? This is kind of fundamental to the concept here. Okay. So in terms of implementing it, over on the left here, typically what's done is every time period you would project ahead for some time horizon. Often it's 24 hours. Kind of the next day you'd predict ahead how things are going to be performing. And you update that every so often. It could be every hour, every 15 minutes. But basically what you're doing is this building optimizer, we'll call it, this model predictive control system, is always kind of looking ahead and seeing what's coming up. And it's also collecting data from sensors in the building and seeing how it's performing, and then trying to, using that information to improve the performance over the next period. So this idea of kind of continuous optimization is implicit in this also. The last slide was kind of giving you a snapshot in time, and this is how it plays out over time. And this is just kind of a representation of the software system. This is a software package that LBNL is developing to implement model predictive control. It's an open source package. So part of the research agenda in model predictive control is using it, or making it easier to use, developing these kind of open source packages to do that. It uses this system called Modelica, which is a mathematical modeling system that you can use to represent the buildings. And so that's the model part of the model predictive control. And then let me give you a couple of applications here. So that's kind of the theory of how model predictive control is done. I'll talk about a couple projects here that LBNL is doing where we're actually deploying this out in the field. This is a convenience store gas station. It's actually located up in Humboldt County. It's associated with a casino up in Blue Lake. I don't know if any of you are from that area or up there. There's a microgrid they implemented a couple years ago where the casino and hotel can island. And this project is going to make it so that the convenience store gas station can also island based on the, or kind of separate from the grid based on the solar and battery storage. So the model predictive control system we're developing for this case is controlling not controlling the solar, but it's taking into account what solar production is happening and forecast to happen. It's controlling the battery charge discharge, and then it's controlling the HVAC, the comfort controls, and the refrigeration in the convenience store. And again, this can actually island, so this is a microgrid technically, but essentially it's a single building. It's a building with some of these distributed energy resources. So in terms of how we actually implemented the model here, this is kind of a schematic for, this is a screenshot actually of the Medallica program. And so you can think of it as, the box here is essentially the model. These little boxes here represent the mathematics, the equations essentially that would be used to model the battery or the thermal zones in the building or the solar array. And there's certain sets of data that come into the models, and then they, churn away, run their equations, and they produce outputs. And so, they estimate what the power for the different components in the building are going to be, and then some of the other parameters like the temperature, the indoor temperature, what the battery state of charge is, the refrigerator and freezer temperatures. So essentially, it takes a time series, kind of a stream of data, flows it into this set of equations, and it does its optimization, and then comes out with what it expects basically the parameters, kind of the state of the building to be over some future time period. In this case, we're running 24-hour forecasts and updating at about every 15 minutes is how that's working. So this model, though, fits within a larger data system. And sorry, this is kind of busy, but it's kind of a complex system. So the idea is that this is all the hardware out there in the building. And there are software connectors that we call drivers, like your software drivers on your computer. And they're interfacing to these different communication interfaces on these different control systems in the local controllers in the building. So you recognize these: Modbus, BACnet, different interface standards. And then that's all relayed through this message bus, which is essentially a secure communication medium. And it could either be stored, or it can be, well, it is stored, and then it can also be used by these different applications. So the Energy Manager, this MPC Pi application that I showed on the previous slide, that's kind of the main function here. But then there are other things like, something listening for DR signals, sending notifications if something goes wrong. So the idea here, kind of the key development here is this kind of common message bus, or middleware we call it, which allows all the different applications to access the data in the same format and have access, kind of have a complete picture of the building, which is really important. You could think of this data storage. This could also be SkySpark. So, if you think of that exercise you just did, in a way, the user dashboard, essentially, you could think of that as the dashboard you were looking at, the SkySpark. In this case, there's also an application running that's constantly kind of looking at the data, getting weather forecasts, things like that, and then generating these optimal set points and then pushing them back out to, for instance, the refrigerator controller or the thermostat or the battery controller, so that these different devices are controlled optimally over time. So just to give an example of this, we're just deploying this actually now, so I don't have any real data yet, but this is a simulation of over 24 hours, one 24-hour period, midnight to midnight. And this is a case showing, this is a time of use tariff that we're using for this test. So the peak charges were kind of in the middle of the afternoon, pretty typical time of use. And so these are the space and the refrigeration temperatures, the individual component power. This is the battery state of charge. You can kind of see it charging up at night and then gradually discharging during the day, and then charging up again at night. And the largest discharge happens in the middle of the day, kind of corresponding to this peak power price. So as you'd expect, it uses the battery to displace grid power that you would be consuming during that high price time. And so this is kind of the end result of all this. This is basically at the utility meter, the power draw. So at night it's drawing the most when the prices are least, and then it kind of gradually ramps down the power until in the middle of the day it's actually exporting power from the battery, which you can't legally do in a lot of cases, but for this simulation we allowed it to export. So this is a pretty simple case where it's just a battery charging based on a time of use price. Just a kind of a test case to make sure that the simulation was working right. But you can imagine with solar, we don't have the solar production here, but with solar producing in the middle of the day, it would be the opposite of this, because your cheapest power is going to be in the middle of the day when you don't have to pay for your solar. So this would be kind of flipped on its head with solar being produced on site. So you'd be charging the battery in the middle of the day and then discharging it probably in the evening when the grid prices are highest. So this is kind of in practice, this is what model predictive control is supposed to do for the building. Another application I'll just quickly talk about here. This is another project we're doing in Oakland, where we're doing kind of similar to that convenience store, solar, batteries, and controlling loads in the buildings, but in this case it's residences. And we're going to take a block of homes and retrofit them for efficiency and to add controls to be able to do demand response with rooftop solar and storage, energy storage at the block level. And so we'll actually be using model predictive control at 2 levels here. One is at the block, figuring out, kind of looking at those utility prices, seeing whether it's high price or low price, do I want to be exporting or importing, and also looking at the demand and deciding whether the storage should be charging or discharging. And then at the house level also, we're going to be installing or replacing the gas furnaces with heat pumps, heat pump water heaters that are going to do both heating in the homes and water heating. And so the model predictive control in the homes is going to be managing those heat pumps to make sure that they're either charging or discharging at the right time of day. So again, this is kind of looking ahead to this future energy system where we have lots of solar out in the neighborhoods. We want to avoid times when all the houses are producing too much solar and it's all going back onto the grid, because that's a problem today with these high solar penetration neighborhoods. So adding local storage to be able to kind of store that and buffer it is important. And then trying to do the electrification in the homes and managing that new load from these new electrical loads, where if you have a gas furnace to do your heating, you're not really concerned about the load because there's lots of storage in the natural gas distribution system. But when you switch over to electric loads, then you start worrying about these cold morning, winter ramp peaks, or hot summer afternoon peaks, that sort of thing. So this is a project we're doing in Oakland. It's still in the design phase, so I don't have results from it, but I just wanted to show another potential application for model predictive control. So that all sounds great, but you guys have worked with real buildings, buildings never behave like you think they're going to. The convenience store, for instance, when we actually got there to install the model predictive control, the HVAC units weren't running properly. There were 2 rooftop units were used for space conditioning. One was carrying all the load, the other one was carrying almost none of the load, balancing problems. So that's one issue with model predictive control, is that even if you have all these smarts, the underlying, the basic systems have to be working properly. And so that's, we still need all the work and the workforce out there really that's doing the commissioning and the retro commissioning and the preventative maintenance and all those sorts of things that this smart control system can take advantage of. In addition to that, just installing it requires some additional configuration, as you can imagine, and then there's some tuning that needs to go on, some commissioning. And so that's kind of another cost or barrier, I guess you could say, to implementing this. And then another factor is that you do need, it really runs best when it has a lot of data to work with. And so there's additional sensors, there's some additional communication that's needed. You need these, smart thermostats and things like that that have some sort of communication interface. And really, this is where a lot of the research is. This is why a lot of this is happening at the lab, is that trying to make these systems that are easier to configure. I mean, ultimately, we want the holy grail to plug and play, which probably, we all recognize will probably never happen completely, but making it easier and easier to install this and tweak a few parameters, and it works well. And then the other is, if I go back to that chart that showed all the communication interfaces to the hardware in the building, just setting up the communications, getting all the data out of these systems with through the network. It took a lot of work just building those drivers, and there's a lot of non-standard things out there. Even if it uses Modbus, every manufacturer has different Modbus registers, and you have to go look at the spec sheet and figure out which register is the case temperature and which one is the compressor run state, or so. One of the other areas we're working on are standards for communication so that across manufacturers, they'll have essentially standardized ways of interacting with the equipment, so that you're not going to have to program it differently if it's a train or a carrier unit or a Tesla storage unit versus another one. And again, that's been a holy grail for a long time in the industry, but there is actually some movement happening in that area, and so ASHRAE is doing some work there, and in kind of the consumer area, there's some work going on with some of the big tech companies. So we're hopeful that in the future there'll be, the underlying kind of process of rolling this out will be easier. So that's all I have. Are there any questions? Yeah.
Can you go back to that slide with the rooftop solar panels on the gas station?
Just the little graphic of this one? Yeah.
So is this new gas station being built, or the existing gas station you are implementing the project?
It's an existing gas station. Yeah. So
the first question I have, is the rooftop ready to handle that load?
The canopy here,
yes.
This load, so the structural load.
Yes.
It was actually, but they had to do a pretty significant engineering analysis to figure that out, and with the seismic load, but they were able to fit I think it's a 60 kilowatt solar array on the canopy of the gas station, and the structure they had to build to hold the panels was pretty significant, but the underlying canopy was able to handle it.
Okay, how about the permit? I don't know what type of gas station is that. If it is ExxonMobil or the Chevron, I know ExxonMobil. I used to work as a management level a little bit. Then everything is strict. I mean, you cannot even change something on the pump without permission.
Right.
You have to call the contractor. So did you go through the special procedures or permit?
Well, this is kind of a special case because I mentioned it's at a casino. So it's a tribe that owns this, and they own the gas station, and they're also their own permitting authority. So it's a special case.
The reason I am asking,
for a research project, is wonderful because we don't have to.
Yeah.
And even with that, it took a while, believe me.
For the future projects, if we can work with those giant companies for the new gas stations or convenience stores, they can mandate or do some incentives to the owners or whoever establishing to have solar panels on the canopy and the EV station. I believe that's the right move, that we need to convince them somehow.
Right, we need to get into their model design for their standard gas station. Yeah, I agree with that. Part of this project, completely separate from the whole model predictive control part, we were doing the lead research institute on this is Humboldt State University. They did a whole study on gas station resiliency and kind of did a survey of gas stations to look at, what sort of systems do they have and what's the potential for rolling this sort of system out across California, and also what the resiliency needs are. Because obviously, with Sandy, for instance, people probably saw the big lines with the gas stations that the power went out and people couldn't get fuel for their cars to evacuate it. So gas stations are really critical infrastructure. So that's part of the thinking of this is, if we can make this so that the gas station can island and keep the pumps on and maybe keep some basic, convenience store operations so that people can buy, emergency supplies or food or that sort of thing, that's a really important function. So that was part of the thinking, but I agree with you that retrofitting these things is really challenging with code and engineering and all that.
Thank you.
Yeah.
I was told that there was 10 kilowatt hours of storage in the beer because you're actually thinking of changing the case temperatures.
Yeah, we are adjusting the refrigeration temperatures within a narrow band, with food safety. It's interesting. There's less thermal mass there than we thought, and it depends some. So these are like walk-in coolers. I think a lot of people have probably seen well, in a convenience store, there's space behind the display racks, and they use that for storage, which I think is pretty common. So you store, mostly it's beverages, right, for a convenience store. So they store stock there and load it into the display racks gradually. So depending on how much is there, you get a different amount of thermal mass to use. But
how many degrees are you changing it?
I think it's funny. We're just working on this. I think there's a 5-degree band that's permissible. So it's like 33 to 38 degrees.
You don't want to freeze the beer.
Yeah, you don't want to freeze it. And the freezer, actually, you get a little more leeway with because there's enough there's enough stored thermal energy in the frozen food, basically.
So it's kind of shipment dependent.
Yeah. And then the other issue is defrost, actually. So the defrost cycle runs on, I think it's every 6 hours. And that's a pretty significant spike, but it's not controlled by, it's not thermostatically controlled like the compressor is. So that's in terms of modeling it and actually developing a model of the physical system, that's kind of a challenge, that the defrost heaters run on a different cycle. But that's the idea, basically, is using either the building itself, or in the case of the refrigerator freezer, the product as energy storage that you can use to shift loads. That's kind of the basic idea. So we have the batteries are energy storage. There's energy storage in kind of the physical things in the store. And then, you can play around a little with the inverter in terms of, curtailing the output of the solar if you have to.
You have to manage the batteries too.
Right. So the battery is, that's a major part of it, because the battery has, it's a pretty big battery for this amount of load. And so it gives you a lot of leeway to, charge and discharge and kind of adjust the load at the utility meter, essentially. Yeah.
I haven't heard any discussion on phase change for storage.
Yeah. So phase change. That's phase. Well, kind of stepping back to Physics 101. Phase change. There's more energy that's either consumed or given off when materials change phase versus just changing the temperature. Right. That's basic physics. So for thermal energy storage, you can either do kind of sensible storage systems, which are just like a water heater where you're raising or lowering the temperature of the water, but it's in the same phase, or you can do systems that actually cause whatever the material is to change phase, to either freeze or to melt. And so there are, if I go back to here, this actually is an ice storage system. So there are commercial systems available that, this is a pretty nice kind of packaged product that internally, makes ice or melts ice. And so the idea is that, during that melting and freezing phase, you can store a lot of energy in there and then draw it out later. Those are, so these systems exist. They've, actually, what is it, Ice Bear, I think, is one of the companies. They've been around for quite a while. Yeah. So I think, those systems, I think they work pretty well. They're not very widely deployed for whatever reason. I think, for you don't, unless you have some sort of utility incentive program where you're getting paid to shed load and paid pretty well, it doesn't necessarily make sense. But potentially in this future world where we have solar on site and you have kind of excess, essentially free solar, it might make more sense. There are also phase change products that are, I think, on the market also. We've done some tests here at LBL with phase change that goes above the ceiling and can be used. That's more like a paraffin material for cooling. And so those sort of systems exist. There are also, I know of a company, a British company that sells heat storage batteries, essentially, bricks that have material that changes phase when heat is added to it. And those can be used for instance, water heating storage or heat storage. So that is some of the research we're looking at also is for these electrified end uses like heat pumps, where traditionally you wouldn't have electricity running, at least in California, for heating buildings. Maybe using heat storage to kind of mitigate that peak, particularly on building startup in the morning, because you can get a real spike in the power draw in the morning. Did that answer your question?
Just curious if you mentioned it a couple of years ago that you were looking at the lab, but I haven't heard boo or any more developments upon different materials with that phase change temperature being in the 68-degree range or some usable where we could line the walls with it.
Right. Yeah, I think there's a few. So the problems with phase change, or the challenges with phase change, let's call it that way, is making it so that you can, ultimately you want it to be dispatchable, right? You want it to suck up energy when you want to store it, and you want to be able to pull it out right away or as quickly as possible when you want to get it out. And with these thermal phase change materials, a lot of times the time constant is just too long. That it, for instance, people have experimented with drywall material that has phase change material embedded in it, and it takes a long time to kind of charge the drywall material and then discharge it, because you're just basically, it's a small delta T, temperature difference you're working with, and so it.
Right, but once you maintain that temperature, that radiant temperature is constant for the human comfort.
It can help with that, with kind of smoothing out temperature swings and that sort of thing. Yeah. And that's why these sort of package systems work well, because you can kind of directly charge the material with, they have cooling coils and draw it out pretty quickly. So, okay, well, I think that, Peter.
Is there any thought to add hydrogen generation and have a hydrogen fuel cell depot as well as part of that?
Yeah, so about hydrogen generation. People are thinking about that, and it's pretty cutting edge at this point. I don't think we're doing we're doing fuel cell research, but not on kind of buildings that are using, for instance, taking solar and generating hydrogen and then running it back through a fuel cell. Marianne, do you know, is anybody here? Oh, with buses. Yeah, not much. It's one of the kind of perspective areas that we're really looking at, because one of the issues with kind of going back to the duck curve, right? There's the daily duck curve, but you also have a seasonal, people don't call it a duck curve, but you get a lot more solar in the summer than in the winter. And so we're going to have to start doing seasonal energy storage. And hydrogen or biofuels are one of the main ways people are thinking about doing that. So in the longer run, we're going to have to probably adopt some sort of strategies like that. Yeah. In fact, in the short run...
That's actually a really good segue to Marianne. Thank you, Rich.